Alright guys, here we're going to talk about electrophilic aromatic substitution, in particular when there is an electron withdrawing group put on the ring. We already talked in class about how electron withdrawing groups will deactivate the ring. They deactivate the ring by making the ring less nucleophilic. If the ring is less nucleophilic, then it will react slower than benzene. Now we're also going to determine the regiochemistry of the reaction. It turns out that most electron withdrawing groups will direct the substituent that's coming in to be in the meta position. I'm not talking about halogens, just talking about a normal electron withdrawing group. So first I'm going to talk about what happens when we put a nitro group on the ring. The nitro group is very electron withdrawing because the nitrogen that is attached to the ring has a positive charge. That positive charge is electron withdrawing significantly. So I want you to keep the fact that the nitrogen has a positive charge in your mind as we look to see what happens during the course of this reaction. So first up, we're going to put the substituent coming in, the electrophile, in the ortho position. That means this double bond here is going to be the one to react. And again, I'm using just generic electrophile. It could be a carbocation for the Friedel-Crafts alkylation, an aselenium ion, Friedel-Crafts acylation, so on and so forth. I'm just drawing it generically. So for the position to go in the ortho to the nitro group, this double bond will react. The electrophile goes to one side. The hydrogen atom is still there. The carbocation would form at that position. These other double bonds would not be touched. There are two other resonance structures that can be drawn. One resonance structure would have that double bond come over. The carbocation would then look like this. The last resonance structure has that double bond moving over as well. And the carbocation would look like this. So those are the three resonance structures if it were going to the ortho position, and we'll discuss the stability of those in a second. Now let's determine what happens when the substituent comes in at the meta position. Coming in at the meta position means that that is the double bond that will react. So the double bond will react with the electrophile. The electrophile will go to the meta position, still has a hydrogen atom there. The carbocation goes to this position here. Those other double bonds remain untouched. As usual, we have resonance structures. So one resonance structure has that double bond moving, forming that carbocation. And then one more resonance structure. Oh, that's the one that goes backwards. Sorry. Then the other resonance structure has that double bond moving over. So then the product, or the resonance structure that comes from there, looks like this. So those are the three possible resonance structures for if the substituent goes into the meta position. Finally, let's draw what happens if the substituent goes into the para position. This is the double bond that is going to react. So the double bond reacts with the electrophile. The electrophile goes to one side. The carbocation goes to the other. These double bonds remain untouched. Like always, we've got tons of resonance, so we can resonate that double bond over. That puts the carbocation there, right next to the nitro group. And then we can resonate one more time. That puts the carbocation there. Now, if we look and determine what's going on with the resonance structures, hopefully, because I pointed out the fact that the nitrogen has a positive charge, this resonance structure is very, very unstable. It is unstable because you are putting a positive charge on the carbon right next to a positive charge on the nitrogen. The like charges repel. So that is a particularly unstable resonance structure. It's very high in energy, therefore it will not form. If we look at the meta substituents, none of them put that positive carbocation next to the nitrogen that also has a positive charge. So none of the meta resonance structures are destabilized. If we look at the para, again, I hope this one jumps out right at you. Once again, you are putting a positively charged carbocation right next to a positively charged nitrogen. Like charges repel. Therefore, that resonance structure is particularly unstable. Because the meta substituent, the substituent in the meta position, does not have an unstable resonance structure, the meta substituent or the meta position is preferred for electron withdrawing group substituents.